I'll move on to the next common question that I seem to be getting as well, and that is, how do you transfer cardiac myocytes from calcium-free to calcium buffers? Now, this, I won't spend too much time on this, but I just want to reiterate the point again, particularly because both Matt and Ronglih have discussed it in this Q&A session, but also Ronglih has discussed it previously in the previous webinar. So just to kind of reflect back on what's been discussed, when you isolate cells, you will isolate cardiac myocytes, which are sort of represented here at the bottom of the tube, as well as other non-myocyte cells. Now, the cardiac myocyte cells, due to their size and weight, will gravity pellet on their own. So if you just put them in a tube with your perfusion buffer, they will come down first, and they will basically form a pellet at the end. And obviously, if you pass a cell suspension through a strainer and allow this gravity settling, in about 20 minutes, you'll see a nice pellet at the bottom of your tube, whereas the supernatant will contain the non-myocyte cells, debris, and some extracellular matrix. So, and the technique that pretty much every lab uses is sequential stepwise addition of calcium, reintroduction of calcium. So going from 0, or in some cases 0.1 millimolar calcium, and then taking that pellet and resuspending it again in a let's say 0.3 millimolar calcium, allowing those cells again, cardiac myocytes, to gravity settle, and then introducing it back again into a higher concentration of calcium, etc., until you actually get to the concentration of calcium that you want to use for your functional or signaling experiments. So I really don't want to go beyond this. I know this is to some extent an oversimplification, but a gradual introduction of calcium is quite important if you want to achieve a high concentration of calcium that your cardiac myocytes are essentially resistant to. And I would probably like this stage now to invite any questions or any further comments from Matt and Ronglih.
I would only add that this is what I was trying to maybe not so well describe when I say this is how you can remove BDM as well. Because at the same time as increasing your calcium concentration, you can sequentially reduce your BDM concentration as well. So at the end, you would have a situation where the cells are resuspended in buff with no BDM.
Yes, yeah, I think that makes complete sense, yes. Ronglih, would you have anything to add by any chance?
I completely agree. And, if people don't want more pure, then I would say, you can take the sedimentation time shorter. So this way you will prevent those, smaller lightweight particle to come down. You will get lower yield, but you get pure. So that's
Sure.
one way try to get pure, but that's just, small differences, but it may matter in some experiments, but the compromise is the yield.
Sure. One thing that I actually would like to get your opinions, both of yours, is normally when we sediment, we use 50 ml Falcon tubes, and you will see the pellet of cardiac myocytes forming at the bottom. Now, we tend to sort of put the tube slightly on the side to increase the surface area of that pellet so that we reduce the chances of hypoxia. Is that something that you will have experienced as well? And would you recommend that to others? Or is this just some of these strange things that we do and think work, but but potentially are not implemented in other labs?
In our lab, we never do that. And like I say, we tend to be, depends on what's the purpose for it. If it's for functional measurements, we will know what's myocyte, what's non-myocyte. But if we take it for culture, which we want to prevent other cells also contaminate, we will reduce the time. So that's pretty much the only thing we manipulate.
So you do not tilt the tubes a little bit, just to fine.
That we have not implemented, but we can try it next time, see what happens.
Okay. Matt?
Yeah, I think it's an interesting point, because what you don't want is that pellet to be there so long that a hypoxia sets in, right? Which I think is what you're getting at here.
Yes.
And I guess that's the same reason why you use a 50 mil Falcon rather than a 15.
Yes, it's narrower, so therefore there's more thicker pellet forms. Yes.
Yeah, so I mean, we actually use 15 mil Falcons specifically because the angle at the bottom of the tube is steeper.
Mm-hmm.
So I guess we're putting ourselves more at risk of a hypoxic pellet then maybe, but otherwise what we find is a lot of our cells, they settle on the
rim,
slide, on the slopes of the 50 mil Falcon tube, and when you're aspirating or whatever you do to take away the supernatant, you can lose some cells that way.
Yes.
I think you have a nice method, Davor, of giving it a little swirl at that point, so they nicely form a pellet.
Yeah, so I would say probably to the viewers,
a video of that.
Yes, I probably would say to the viewers, if they do see that the cells are sort of depositing on the rim of the 50 mil Falcon tubes, you can introduce a really slight vortex, and then the cells will sort of really deposit slowly into the center of the tube within a minute or so. So that tends to work for us here, but but that's something that Matt and I have just discussed probably a week ago when you visited here.
Yeah, that's right. Another thing I actually use, so rather than the 15 mil Falcon tubes now, I actually use the 10 mil or 15 mil mini prep tubes. You know, the ones which you often do your bacterial mini preps in.
Yes.
So they're quite nice because they have they're effectively vertical all the way down, and then they have a round bottom which without much without a gradual rim, and so all of your cells they do collect right at the bottom, but not in such a big pellet with a kind of potentially hypoxic core. It's more a gradual all around the bottom of that tube, and they're also much cheaper. So it's two advantages then. If you can get your hands on those, I think that's what we tend to use ourselves now.
I think that's a very good suggestion, actually. Yes, I remember you were mentioning that to me, so we should definitely try that.
Yeah, give that a go.
Great.
Actually, the graphic showing here is more that kind of tube.
Exactly.
Yeah.
But this is I take no credit for this. This is actually Matt's graphic. So he was obviously foreseeing the problems in the future when he designed this. So
yeah, I had too much time on my hands.
No, it's very good. Well done.
I think we should just emphasize that point though that you made. Once a pellet has formed, don't wait too long before transferring it to the next tube and resuspending, because you don't want a hypoxic pellet sat around too long, right?
Yep. No,
so I think these timings for gravity settling, they can be flexible. I think we put in our paper it's 10 minutes for each settling, which usually works pretty well. But if for whatever reason they're settling more slowly or faster, you know, if you have a very big pellet there after just 5 minutes and that's all the cells you need, just go ahead with that. You don't necessarily have to wait for the full 10 minutes because you don't want your pellet sat there and becoming hypoxic or whatever. You know, if you have enough cells, then just go with that, I think.
Yes, no, I fully agree.
Actually, I want to comment on sedimentation time. I think this is actually, if the cell prep is good, actually cell will settle pretty readily. I mean, I don't have on top of my head the timing to say, but they are settled quite fast. But for those actually settle too slow, or in fact, it's too fast, both sides are no good. And so generally we wanted, you know, kind of how you gauge it, like literally, if they're going to be a good myocyte, in a couple minutes, they should be all fall down. And we tend to try to grab that and go into the next concept.
Okay, that's interesting.
You see the yield will be lower, but the cell will be better. So again, it really depends on what you want to do with this. If you want to do myocyte contractility, which you will put myocytes already, back into the system, then the myocyte shape and you already can select from there. But then if you do biochemistry, molecular biology, I think, you don't know what's your contamination until you really measure it, right? So I think this will give you maybe the yield is lower, but it's more higher percentage is cardiomyocytes.
Yes, yeah. Although I suspect to some extent you would select the larger cells then. So you would get the larger cells settling first. So
yeah, that's true.
You would skew your findings.
Yeah, it's a timing issue. People can sort of try and error and work out their own condition.
Yeah, no, that completely is sensible and logical.